Hey, welcome back for lesson 34, which is a quick look at the graph for the photoelectric effect. Now the first thing is there's about 5 key points on the graph that you need to remember. So if we pan down and look at the graph real quick here, you'll notice that the vertical axis is energy. This is like the kinetic energy of the electron. So if an electron is hit with enough energy in a photon or in the quanta, it can escape where it's sitting and actually physically move. So that's kinetic energy. Along the bottom here is the frequency. So as the frequency increases, the wave itself gets smaller, so a smaller wavelength, but that's a higher energy wave. So the bigger the wavelength, the smaller the frequency, the lower the energy. The higher the frequency, the smaller the wavelength, the higher the energy. So at a particular energy or at a particular frequency, there'll be enough energy in the packets or the quantas, the photons, to cause the electrons to move. Now down here at the bottom where it touches the graph, that's considered the work function. We'll talk about that later. And then you'll notice, of course, that there's a particular slope for this thing. This is Planck's constant. Now because everything adheres to Planck's constant, that means the slope has to be uniform or the same for all graphs. If I were to draw multiple lines on this graph, they would all have to have the same slope. Now let's quickly look at the different points. So as mentioned before, the threshold frequency is the amount of energy or quanta in a particular wave in order for it to cause an electron to move. So simply put, if the photon doesn't have enough energy, it'll merely bump into the electron, but not cause it to actually jump out of its orbital and make it free-flowing like electricity. Now the next variable is the work function. The work function really is the distance that the electron has to travel up the hill, or you can imagine it like a hole that the electron is in, and it's the distance that the electron has to move to get out of the hole. Now if you look at the graph here, because the work function really represents from the 0 point down to a particular point, you can imagine its rise, one value being 0, the other being some number. Think of that as the height of the hill or the depth of the hole. You need to put a minimum amount of energy just for that ball or the electron to reach the top of the hill and get over, in which case where it would be able to then travel forward. Or if you think of it like a hole, if the electron only jumps to a certain height, it never actually gets out of the hole. It actually has to reach that minimum threshold height or threshold frequency before it can actually escape out of that hole. Those are probably the two best analogies for understanding the work function. Now, of course, the next is the Planck's constant, which is really just rise over run or the slope of the graph. If you remember back with Planck when he was talking about this, energy doesn't just flow in unlimited amounts in any kind of a stream. It actually has to move in particular packets. So depending on the wavelength, these packets will vary, but there's kind of a variable or some kind of constant by which the energy changes. This, of course, relates directly to Planck's constant. So it's always the same value on the graph. Now, if we look at this graph, we can see we have 3 different lines. We've got the blue line, the red line, and the green line. Each line represents a different metal or a different substance, and of course, each one has a different threshold frequency. So, of course, the blue has the lowest threshold frequency, and the green has the highest threshold frequency. If we were actually to continue down on the graph on the vertical axes, we'd also notice that they'd have to hit the vertical axes at different points, meaning, of course, they have different work functions as well. The blue, of course, calcium has the smallest work function because it hits the vertical axes before the green line would, or again, the amount of height or negative height. It's also worth quickly mentioning that you notice that the slope is, of course, always the same because they all apply to Planck's constant, which is the slope. Now, the last little bit about the photoelectric graph is the mathematical equation to work with it. Really what it is y is equal to mx plus b, the standard slope graph. However, each value y, mx, and b have different things. The other way of looking at it, of course, is saying Ek max is equal to hf minus w, so that the energy that the electron has is related to its frequency in Planck's constant, minusing a w, the value that's underneath. Another way of looking at it is the formula above, keeping everything on the positive so that there's no negative symbol in the graph. It just says hf is equal to Ek max plus w. So if you look at the graph again, hf is equal to the energy that the electron has plus the work function, which means this. The frequency, which is maybe somewhere over here or wherever it is, has 2 parts. The part above, which is the energy that the electron has, and then the part down here in this area, which represents the work function. So basically, if you add this to this, that's representation of everything on the graph. And that's what the formula says. The total area here on the graph is basically the area above plus the area below. Now, while this equation isn't on your formula sheet, I highly recommend that you add either this top one or the bottom one here. It'll make it a lot easier to do the formula work because the graph itself and this formula really aren't too difficult as long as you remember these basic principles that we've talked about in today's lesson. So really, as I've said many times before, go have at her, try some of the different equations, try and work through this equation. I'm sure you'll be able to figure it out in no problem flat. All right, we'll see you on the next one.